which was formulated in the same paper where they show for first time a relation between these coefficients and these rational points on elliptic curve. So now I will try to make everything more precise. So, okay, so the aim is to study. Aim is to replace this Kohnen lift with the generalization of it, which is due to a work of Baruch and Mao, and to explain. So this is and to explain the relation between these Fourier coefficients and the points on elliptic curves. Okay, so this is the aim. And I should say that this is a work in progress with Zhengyu Mao from Rutgers. Okay. Okay. So first, let me recall what is a half-integral modular form. So half-integral modular forms. So for this, we fix an integer k, non-negative, and we fix an m positive odd integer, and fix a character chi from z mod mz Dirichlet character, such that the chi of -1 is equal to +1. So we require this condition. And then a cusp form of weight k plus 1/2, level 4m, and character chi. And character chi. But it's just an holomorphic function. G from the upper plane such that the following conditions are satisfied. So the condition is that so for each matrix sigma, which is A, B, C, D in gamma 0 for M, we have that if we apply G to A Z plus B over CZ plus D, this is equal to J sigma Z, which is the automorphic factor, to K plus 1, chi D, and GZ. And this automorphic factor can be described as follows. So the transformation rule essentially says that this is transforming as the power of the transformation formula for the theta function. Okay? So, sorry? Ah, yes, sorry. Okay, so the transformation formula is so the automorphic factor is this. This is theta, the theta function, A z plus b over cz plus d over theta of z. And the theta is the theta function. So it's the sum of e to pi I and square z. Okay, and plus, of course, some vanishing conditions at cusps. So each such modular form can be written as a power series expansion, n greater or equal to 1, Cn q to the n. And we write this space as k, s k plus 1/2 gamma 0 for m and character chi. Okay, this is the notation, and then I would like to talk about this generalized Cohen lift. So we introduce this Cohen lift, at least generalization of Cohen's lift. So for this, let f, so generalized Cohen's lift. This is a work of Baruch-Mao. And this is as follows. So let f be a cusp form of integral weight k and level gamma 0 m. And we assume that m is here is square free. And now we fix a divisor. S dividing m. And also we fix a Dirichlet character chi from z over 4 m s z star to c star, such that the key component of this character is equal to -1 if p divides s, and chi of chi of -1 is 1 plus 1. Okay, so these are the conditions. And then under these conditions, sorry? This is sorry. Yes, thank you. This must be -1. Sorry. Thank you. Okay? So, under these conditions, there exists. So, under these conditions, then there exists a unique up to scaling form, which we call GS, which we write as C n q to the n and greater or equal than 1. And this belongs to, is an half integral modular form of weight k plus 1/2. Okay, yes, it's okay. And level gamma 0 for m s and character chi, such that the following is true. So the first thing is that GS is a Shimura lift of f. So GS is a Shimura lift. By this we mean, we just mean that f has the same the GS has the same eigenvalue as F under the action of F operator. So it incorporates the eigenvalues of the modular form F. And then, second condition is that these coefficients, Cn, are always 0 when, so -1, little s, I write little s for the cardinality of primes dividing S. -1 to the S plus k half. This, when this is not congruent to 0 or 1 mod 4, and so here we note that we start with the modular form. Okay. So the third condition is that so if say that d times -1 to the s plus k half is a fundamental discriminant of a quadratic field, and C of D is non-zero, then we have that D over P is equal to minus WP if P divides S, and D over P is equal to plus WP if P divides M over S, where WP is the sign of the Atkin-Lehner involution on F. And finally, we have the most important, so these are just some technical conditions somehow, but the important condition comes now. So why this is called generalized Cohen lift? Because it interpolates special values of L series. So now I'll be more precise on this. So if -1 to the S plus 1/2 is equal to the sign of D, then we have that, so if I look at the Fourier coefficients at D square divided by some Shimura periods, GS, the Peterson product, sorry, this is the L value of F, of the L function of F, twisted by the character chi D, and, I'm sorry, here there is a K, sorry, K half. Okay, twisted by the character chi D over FF. Remember that F has weight 2K in this. And then we have some other factors, which are K half minus 1/2. And then we have, so we are talking about central critical points, because F has weight 2K, okay? And then there are other factors like K half minus 1 factorial over some power of pi. And then we have this P to the P minus 1, where the product is over all primes P dividing S. So what this formula says is that these Fourier coefficients of these lifts incorporate special values of L series. And for S equal to 1, this is Cohen's result. Okay? And the other condition is when this doesn't happen. Well, when this doesn't happen, the special value vanish. Okay, so if, so maybe number 5, if minus 1 S plus k half is different from the sign of D, then the special value vanishes. So F, KD, and K is 0. Okay, so this is the kind of lift and the characterization of the lift that one wants to consider. And as you see, the type so the vanishing or non-vanishing of L values depend by some parity conditions. So it is somehow natural to divide discriminants, fundamental discriminants, in two categories. Those for which the L function vanish and those for which doesn't need to vanish. Okay, so this doesn't say that it vanishes, but one expects that it doesn't vanish several times. So the types of discriminants that we are going to consider can be divided into the two. So it's more or less natural from this from what I said to consider two types of discriminants. Okay? Fundamental discriminants of quadratic fields. So for this, let F be the modular form associated to my elliptic curve, initial elliptic curve. So this is in gamma 0 NP. So this NP will be my M of the above result. And so let D be a fundamental discriminant of a quadratic field, such that the following conditions are true. So the first is that D over L is equal to minus WL for all L dividing S. And the second condition is that D over L is plus WL for all L dividing M over S. Okay? These are the two conditions which says that we are in position to apply the above result by Baruch and Mao. But then we need the third condition, sorry, which was listed there. So minus 1 to the minus 1 to the S plus 1, this will be equal to the sign of the discriminant D. Okay? And now we say, so we divide now these discriminants in two categories. So we say that D is of type 1 or 2, accordingly with the following, with its behavior on the primes P, which we didn't consider up to now. Okay? So we imposed conditions on primes dividing S, prime dividing N, but not S. So we now consider the prime P. And we see that the first type are those for which D over P is equal to WP. And the second are those for which D over P is equal to minus WP. Okay? So why I'm interested in this definitions? Because you see that if a discriminant is of type D, then from the above theorem we see that the special value of the L function of f twisted by character chi d and the central point 1, this is necessarily 0. Okay? So this is the Baruch-Mao theorem, which says this, that the special value is 0. And on the other hand, if instead of having a discriminant of type 2, we have a discriminant of type 1, we know from non-vanishing results, so maybe I will write this in another blackboard. Okay, so for discriminants of the second type, we know that the L value vanishes. While for discriminant of the first type, so moreover, we can, so let's say by non-vanishing results for L functions twisted by characters, we can find some D0, fundamental discriminant of type 1, such that so the Fourier coefficient C attached to this D0 is non-zero, and we fix such a D0. Okay, so this is our setting, and now, so now I talked about the general Cohen lift for a general modular form to modular form of half integral weight. I connected Fourier coefficient with the vanishing or non-vanishing of special values, and I introduced two particular kind of fundamental discriminants. Okay, so no families up to now. So now I would like to insert my modular form on an Hida family, and see, and then state the result which I'm interested in. So I will introduce the notation for Hida families now. So for same notation as for my fixed modular form, so n is an integer, which is square free and odd, and p as above is a prime which doesn't divide n. So I introduced the weight space as this X to be the continuous homomorphism from ZP star to ZP star, which one may identify with the ZP cross Z over P minus 1 Z. Okay? And Z sits inside X by taking K and sending it to the homomorphism, which takes X to X, the K minus 2. Okay, so we have some integer, which will be our classical points in my weight space. And now I state the relevant part of Hida's theory, which is relevant for us. So Hida there exists U, a neighborhood of 2 in X, which we assume contained in the residue class of 2 mod p minus 1. And there exists a formal Fourier expansion x infinity of k, which is the sum of a n k q to the n with n greater or equal than 1. And here the a n are, maybe I can do, and here the a n are rigid analytic functions on U, such that the following is true. So such that the first condition is that for each k, which is an integer, z greater or equal than 2, which is also in this U, we have that if I evaluate f infinity at k, this is a modular form of weight k and the level gamma 0 and p. And of course, we want that f infinity of 2 is our form f. Okay? Okay. I have always some troubles with the backboards. Okay, so now, of course, the modular form f is a new form because it's attached to our elliptic curve, which has level conductor and p. But the modular forms here, appearing here, fk, are not new forms. And we can consider fk sharp to be a modular form of the same weight k on gamma 0 n with p removed, such that f is the p stabilization of fk sharp. This just means that fk z is fk sharp z minus the eigenvalue of the p echo operator at p times p the k minus 1 times fk sharp of z. Okay? Okay, so now what we have, we write, okay, so we have our f, and we can associate by this generalized Cohen lift a modular form, which we write as g, which is g which depends on s, which is a cn q to the n. And for each of these members k sharp, with k here, of course, greater or equal than 4, okay? Even integer greater or equal than 4, we can associate this gk, which is sum of cn k q to the n, okay? So we have this lift. We can lift each member of the family. And it's not strange that since they come from these are values of rigid analytic functions, somehow these are interpolated by these rigid analytic functions, then the same will be true for the coefficient of the generalized Cohen lift. Okay? So more precisely, we have the following. So we have the following p-adically interpolation process. So p-adic interpolation process, which is the following. So we can define the normalized Fourier coefficient for, so here k will be an integer, strictly greater than 2 in U, as so C tilde d of k, d will be as above fundamental discriminant, and this will be 1 minus 1 to the s plus 1 d over p. Then we have p k minus 2 half over apk, and this will be multiplied by the Fourier coefficient of cd of k, which is that coefficient for the forms with sharp, and over the same thing evaluated on the fixed discriminant d0, which we choose such that c of d0 will be non-zero. So minus 1 to the s plus 1 d0 over p to the k minus 2 half over apk, and then c d0 k. So we can define these normalized coefficients, and the proposition is that this coefficient extends to p-adic family. So more precisely, so the function k, let's say this is a proposition, the function k in c tilde d k extends to a p-adic analytic function on U with the property that such that, so this is defined for k greater or equal than 4, I mean k greater than 2, okay? So one wonders which is the behavior at 2, and thanks to the Shimura's relation for half integral weight modular forms, one can show that actually the value of 2 of this function is just the quotient of CD over CD0, okay? Okay, so in particular what we see? We see the following. So the remark, which is the crucial observation for what I'm going to say, is that, now suppose that D is of type 2. So suppose that D is the discriminant of type 2. Then we know that the L series vanishes of F. And this also shows that, gives us that the Fourier coefficient at D vanishes, okay? This is the result of Baruch-Mao, which I mentioned before, because it expresses the, this is the observation we already did. Okay, however, since, so this is of type 2 relative to the form F, so to say. But when we look at this D relative to the form Fk, where we removed P from the level, we don't, we see that this D is somehow of type 1 relative to the forms of level greater than 2. I mean, the forms of level, our fixed modular form F has weight n times P, okay? So the fact that the L value vanishes depends on the fact that we choose a certain condition at the prime P, okay, for the relative to the sign of the Atkin-Lerner involution. Okay, the modular forms Fk sharp, we have level n and not np. So these are not sensitive with the choice we made relative to the Atkin-Lerner involution at p. So there is, so this says that there is no reason for the function k to c tilde d of k to be 0 on all of u. So what happens is that this function, and for non-vanishing results for L series, it will be non-zero. Okay, so what happens is that this function we constructed here, k in c tilde dk, is 0 on 2 and non-zero on neighborhood. Okay? Oh. Okay, so it makes sense to consider its p-adic derivative somehow. Okay? So, and now it's time to say which is the result which proves this conjecture of Darmon-Tornaria. So the result is this one, justified by the above considerations. So the main result is this following. So the main result is this one. So you fix phi Tate, the Tate uniformization of the elliptic curve from Cp star over Q to the Z to a Cp. And we fix a branch of the p-adic logarithm such that log Q, such that log Q of Q is 0, where Q is state period. And then we can define a logarithm of on the elliptic curve, log E of the elliptic curve from, let's say, the Cp points of the elliptic curve by taking a point and evaluating it at the log Q of phi Tate minus 1 of P. Okay? Okay, so the first theorem I want to, I don't know if I will be, if I will also state theorem B, but let me state theorem A is the following. So let D be of type 2 with respect to our fixed S divisor of N. So the first relation is that the p-adic derivative of these coefficients evaluated at 2, this is the logarithm of a point which depends on D, and which is PD will be a rational point on an elliptic curve, Q. Maybe I will forget some integrality property by taking tensor it over Q, and then PD as a point in that Q vector space is non-zero if and only if the special value of the derivative of the series is non-zero. So we know that the special value of the L series is 0 by parity reasons, as I observed. So we know that special value is non-zero, so it makes sense to is 0. Sorry, so it makes sense to consider its derivative. So the point is non-torsion if and only if, which is a kind of Gross-Zagier formula. Okay? So I will just, so this result depends crucially on a result of Bertolini and Darmon on 2008 on the rationality of Stark-Igner points over for genus fields or Lie quadratic fields. Is somehow a combination of this Bertolini-Darmon result, Bertolini-Darmon result, plus some, combinatorics, some work started from this Baruch-Mao work. So this is the first remark. The second remark I want to make is that for S equal to 1, so in which case, in this case, we have the classical Kohnen lift. I mean, the Kohnen lift studied by Kohnen, the lift studied by Kohnen. So in this case, the same result, or the similar result, has been obtained by Darmon and Tornaria. And they made a conjecture, and the shape of the conjecture of Darmon-Tornaria was the following. So this kind of points, the logarithm of this kind of points can be always defined independently of the parity conditions that we imposed on D, okay, somehow. Or at least under those conditions that we imposed, which generalize the parity conditions imposed by Kohn for his lift. So this point can be defined. So the conjecture was there exists a lift such that this holds. Okay. Okay. So let me just give very quickly the idea of the ingredients that are used in the proof. Okay. Problems. Okay. So the main ingredient that is used in these proofs, in all these kind of proofs, are p-adic Shintani integrals. So p-adic variation of classical Shintani integrals. Okay. So what is a Shintani integrals? So Shintani integrals. So for k greater or equal than 4, and always k an integer in my U, so we consider J the function depending on k on polynomial P, which is a polynomial of degree less or equal than k minus 2, and depending on R and S, which are points on P1 of Q. And this will be some factor, a1 minus a p to the k minus 1 p to the k minus 1 over some Shimura period attached to fk sharp, and times an integral, which is the integral from my points R to S of fk sharp z, my polynomial pz dz. Okay, so the basic observation which was done by Bertolini and Darmon was the following. So if we fix tau a point in the quadratic ramified extension of QP, which I denote QP square, then the function k into j k z minus tau to the k minus 2 rs extends to a p-adic analytic function on U and vanishes on k equal to 2. So the point is that these Shintani integrals are connected with half-weight modular, the Fourier coefficients of our half-weight modular forms from one side, and from the other side they are connected to global points on elliptic curves. Okay, so I will just fix the notations. So for this now we fix delta less than 0, a fundamental discriminant of a real quadratic field of type 2, and delta prime fundamental discriminant of type 1, and we take delta to be the product of the two, which will be a positive integer. So our assumptions imply the following: imply that if L divides L, then L is split in our quadratic field Q of square root of delta. This is the first thing, and the second thing is P is inert in Q of delta, square root of delta. Okay, and here we make the observation that under these assumptions, so under these conditions, so we expect from the Baruch-Mao conjecture to have a non-torsion point on E of Q square root of delta. And somehow this is the opposite of the situation where we have imaginary quadratic field. Okay, so for the imaginary quadratic field, the usual Eigner hypothesis is that all primes dividing the level should be split in a quaternion in our imaginary quadratic field. Okay, for real fields, real quadratic fields, the change of sign at infinity is so to have the correct sign of the functional equation to expect to have a point, of the L function to have a point, we need to also assume that at least one prime is inert instead of split. Okay? For example, in the case where the discriminant is prime to the level of the modular form. Okay? So in this case, we expect to have a non-torsion point, and okay, which is what we already expect because we know that in this condition the L function vanishes. Okay? As we observed before, because D is this discriminant of type 2. Okay? Okay, so let now chi be a genus character of this real quadratic field Q square root of delta attached to the pair of Dirichlet character chi delta and chi delta prime. Okay? So we have, so in this condition we can form, we can consider this object J of F delta delta prime. I will be maybe not very precise in this, but let me try to be compact. So I will consider the sum over all quadratic for integral quadratic forms, binary primitive integral quadratic forms of discriminant delta equal to delta, primitive integral binary quadratic forms, which leaves in so the isomorphism classes of, let me write, primitive binary quadratic forms of discriminant delta, modulo plus some congruence conditions, which I'm not going to write, modulo the action of gamma 0 m n. So the isomorphism classes of this thing, which is identified with the, by class field theory, this is identified with the Galois group of the Hilbert, strict Hilbert class field of our quadratic field Q square root of delta. Okay, and essentially we take, so this means that if we fix a genus character of this quadratic field, it makes sense to evaluate this on this quadratic form. And we consider the p-adic derivative of these Shintani cycles, which I denoted before as k. So here we need tau q, which depends on q. I will explain how to choose this point. And the extremes of integration are any rational point R. You will not read here, probably. Sorry. I will. R and gamma Q of R. Okay, so I'm going to explain this last ingredient. So gamma Q of R is a generator of the stabilizer of the action of gamma 0 n on my quadratic form Q. And gamma Q is one of the two fixed points for, I mean, you factor Q into two quadratic form, into two linear forms, and gamma Q is one of the two elements appearing here. And since P is inert in K, one can show that actually this tau Q belongs to the quadratic ramified extension of Q. Okay? So this is the kind of object which is related. So from one side, so essentially this we are evaluating this quadratic form. We are integrating this quadratic form along some geodesic cycle, okay, along the upper half plane. So this is a more natural way somehow to understand this these Shintani integrals, and the geodesic cycle is connecting R to gamma Q of R, okay, and depends on the quadratic form Q that you are choosing. And sorry, so this is connected from one side to our coefficients C, D of K, or at least their derivatives from one side, and from the other side, thanks to this work of Bertolini-Darmon in 2008, I think. So this is connected to some points, rational points on elliptic curve, okay? And so this is somehow a way to express these coefficients in terms of these points. And let me conclude with somehow a formula for my theorem B, which is, so if D1 is of type 1 and D2 is of type 2, one way to resume the above result is that, so this series with these coefficients, D2, D1, Q to the n, this is a multiple of the the generalized Cohen lift of f. Okay, and is non-zero precisely when the special value of the derivative of the L series doesn't vanish. Okay, so in somehow one can understand this result as a in Kudla program, so a kind of p-adic generating series for this modular form. Okay, so